Okay. I'm about to pull it together.
These are pencils, but they're stir sticks.
They are stir sticks.
Right with that.
There's pencils right there. Okay, so do you have a convincing argument? So which one has more bananas? Or banana? Okay. Take a stand. Who wants to take a stand on one side or another? And not debate an independent. Okay, Jessica. We'll come to you guys in a minute. Okay, did everyone hear what she said?
No, I can't.
No, because we were all talking.
The top one has 50% banana and the bottom has 40%.
Okay, so the top one has 50% banana and the bottom one has only 40% banana. Do people agree with that?
Yes. You're asking how many more bananas, not
I'm asking which one has more bananas.
bananas.
Not percentage of bananas.
Yes.
It's open for debate, isn't it? I deliberately left it vague in order to have a question so that we could, it's a kind of common question, right? And we deliberately leave it vague so that we can have this very common question. When we think about more of something, some kids think additively. Remember I told you, I think I told you this story about the kids who multiplied 5 times 24 and wrote out 24 plus 24 plus 24 plus 24 plus 24? Yeah. Or some of them wrote out 5 plus 5 plus 24 times, which was a little bit more interesting for me. The problem is they haven't moved from additive thinking to multiplicative thinking, okay, or proportional thinking yet. And when we get into middle school, we hope that kids are moving from additive thinkers to multiplicative thinkers. When kids start thinking multiplicatively, then they can do proportional reasoning. That's what we're going to talk about today. And it's really important that they're able to do proportional reasoning because it appears in so much of what we do with higher levels of mathematics. Okay? If I had said to you, these are packages of fruit. They come in 4 packs and 5 packs. One of the 4 pack is 2 bananas and 2 apples, and the 5 pack is 2 bananas and 3 apples. And you need to buy these. The cost is going to be the same regardless of which one you buy, because we'll say it's $1 per piece of fruit. And you needed to buy them for 100 people, but you know a lot of the people there like bananas. Which set would you buy? The first one. Because in the long run, if I start putting these together, if I had 100 pieces of fruit made up of the 4 packs, so I'd buy 25 of them, right? And I'd have how many bananas? 50. And if I bought 20 of the 5 packs, how many bananas would I get? 40. So proportionally, this one is going to give you more bananas. Okay? So that's one of the types of ratio and proportion problems that are fairly common in mathematics. Looking at kind of comparing different sets to figure out proportionally what's more. Okay? So I put a little web up here. Ratio is an important idea. I would say that probably from grade 6 to 9, it's one of the most important foundational ideas we develop. Grade 8, currently in our curriculum, is a very big year for proportional reasoning. If you look at what we do in grade 8 in our current curriculum, it's all about proportional reasoning. Okay? There's lots of fractions and rational numbers, lots of ratios and proportions. There's dilatations, right, which is an enlargement of a figure, which is really just about proportional reasoning. Okay? So we do a lot of it. A ratio is a multiplicative comparison. So it's when we multiply a set by another set. One of the most common words we use when doing ratios is for every. Right? For every boy, there are about 7 girls in this class. Right? For every dollar I earn, I give 40 cents of it to the Canadian government. For every, right? Those are proportions. Okay? And so it's a multiplicative comparison. Okay? And we can write them as part to whole or part to part. So a part to part, remember I just said for every boy, there are 7 girls, approximately. Okay? So that is a part to part. It's boys to girls, right? For our fruit, we could have written it as bananas to apples, or apples to bananas. It doesn't really matter. What does matter, though, is that we put them in the right order. Sometimes kids will write the proportion and then change the order of what they're talking about. So you have to be careful that they're putting them in the same order, that what they say verbally matches what they've done symbolically. You also could have a part to whole. So a part to whole might be there's 1 boy in every 8 people in this class, right? So that's a part to whole out of the whole, 1 out of every 8, which is more like a fraction, right? So a part to whole ratio really is a fraction. So a fraction is a special kind of ratio. It's a part to whole ratio. Okay. And later on we're going to talk about percents. And percents are a special ratio. What's special about percent? What are they always compared to? They're always compared to 100. So a percent is a multiplicative comparison to 100, which represents the whole. Okay, so it's a special kind of part to whole ratio. It's compared always to 100 parts. So we take the whole, we break it into 100 parts, and we talk about how many of those parts we're considering. Right? And all of these things, the ability to use these is all related to proportional reasoning. And you will be amazed at how many kids in middle school don't have that proportional reasoning yet. Okay? And what we need to do is we need to give them lots of experiences to think about modeling, to think about building bigger sets, right? Enlargements. You ever think of like taking a picture and making it bigger, right? Enlarging it. You're using proportional reasoning when you do that. A really fun activity that I did with my grade 8s one year was making mini-me's, right? So you had to make a drawing or a model or something that was a certain percentage of you. So you had to make all your measurements and then make your mini-me. And you had to draw it. And one kid built it a copper up in the shop, which was really cool. But that whole notion of kind of thinking of scaling up or scaling down is a nice way to think of proportion.
Do you ever do anything with maps?
I haven't, but you could absolutely use maps. You could do lots of kind of scaling things, anything where you're creating a map and you have to scale it down or scale it up. Even like those little drawings that you used to get in the coloring books when you were a kid where it gave you the little grid with the picture and then you had to redraw it bigger, that's proportional reasoning. It's about enlarging something. Yeah, there should be. Does anyone have extra handouts at their table that they're not using? Oh, look, there's a bunch right there. see for modeling ratios are the two colored counters, right? So if I were going to talk about this one, I'd have 2 yellow for every 3 red, so I could talk about it as a part to part. Okay? Or I could talk about it as a part to whole. 2 yellow in every 5 counters. Okay? Or I could talk about the red as a part to part. So there are 3 red for every 2 yellow. Or I could say there are 3 red.
What did you call the third one? A part to part?
This one and this one are part to part.
Yeah.
And then the other 2 are part to whole. So this is part to part, yellow to red. This is part to part, red to yellow. And so it's important that we make sure that what we're saying matches with what we're writing. Okay. And we can make equivalent ratios by just taking these and replicating them. It's still 2 yellows for every 3 reds, but it's also 4 yellows for every 6 reds, which is an equivalent ratio, right? So equivalent ratios, just like equivalent fractions, have that same multiplicative relationship. You can double both values and get an equivalent ratio, or you can triple both values and get an equivalent ratio, right? So there's always this notion of kind of, this is one thing that kids have trouble with, because with equivalent fractions, we've always been cutting them into smaller pieces to find the equivalents, and in this we're actually creating more. So the whole keeps getting bigger, right? Like we keep making more of something, but the proportion stays the same, right? The relationship between the 2 parts stays the same, but the whole keeps getting bigger. So it can throw kids off sometimes. Okay, so it's important that we expose them. Grade 6 is really the year where we start ratios. And we introduce the notion of a fraction as a ratio, right? We've done regional models and set models before that, and linear models. But in grade 6, that's when we really introduce the notion of a fraction that can be a ratio or a rate. Okay? And this is a good example of how a ratio can be displayed in a graph. This tells me the amount of water I need for the cups of rice I'm cooking. Okay? So for every cup of rice, I need 1.5 cups of water. So if I have 2 cups of rice, I need 3 cups of water. If I have 10 cups of rice, I would need 15 cups of water. So it's 1.5, right? So we could write that as a ratio of the water to rice is 3 to 2. Okay, so water to rice, or we could write it as rice to water is 2 to 3. Or we could have written it as 1 to 1.5. Okay, that's the one instance. We normally only use whole numbers, but it is okay to say 1 for every 1.5. Right? But normally we'll convert it into something with whole numbers. Now, what do you think this might be important for later on? I think I heard someone say it. What does that remind you of? Every time I go over 2, I go up 3. Slope. Rise over run, right? Slope. So this proportional reasoning feeds into the work we do with linear equations later on, right? It's an important understanding. No, actually we start teaching linear equations in grade 8. So when we do proportional reasoning in grade 8, linear equations are in there as well. And we do a lot of graphing these proportions to show that, hey, look, it's always going up at the same rate. Okay, slope is literally a rate. It's a rate of change. It tells you how it's changing, right? So this is going to equate with what we do later with slope. Okay, there are different kinds of ratio and proportion problems. So I want you to flip to the next page, or the next box. Sorry, just go down to the next box. And it says, if Sam drove 270 kilometers in 3 hours, how long will it take her to drive 650 kilometers? So as a group now, I'm going to get you to work that out. Take a few minutes at the table.